Everything you see in the night sky is less than 5% of reality. The rest, over 95% of the cosmos, is a total mystery composed of something we call dark matter and dark energy. By the end of this journey, you will have explored 30 of the most compelling and bizarre theories scientists have proposed to explain this cosmic missing energy. We will venture from Einstein's greatest blunder to the possibility that we live inside a simulation. What kind of universe do you think we are actually living in? Our story begins not with a discovery, but with a retraction. Albert Einstein, trying to describe a stable and unchanging universe with his revolutionary theory of general relativity, found his equations predicting a cosmos that was either expanding or contracting. Unsettled by this idea, he introduced a fudge factor, a mathematical term he called the cosmological constant. This was a repulsive force, a kind of anti-gravity woven into the very fabric of empty space, designed to perfectly balance the inward pull of gravity and keep the universe static. He later called this his greatest blunder, but decades later, when astronomers found the universe was not static but rapidly expanding, the cosmological constant was thrown out. Now, fast forward to the late 1990s, when observations of distant supernova revealed something even more shocking. The expansion of the universe is not slowing down, it is speeding up. Something is overpowering gravity, pushing galaxies apart at an ever-increasing rate. And suddenly, Einstein's greatest blunder did not seem like a mistake at all. The cosmological constant was resurrected as the leading candidate for dark energy. The idea is that empty space is not truly empty. According to quantum physics, a vacuum seethes with a mysterious background energy, a constant hum of particles flickering in and out of existence. This vacuum energy would produce a repulsive force, exactly like the cosmological constant, driving the accelerated expansion we observe. It is an elegant solution, a number you can plug right into Einstein's original equations. But there is a colossal problem. When physicists calculate how much energy this quantum vacuum should contain, the number they get is wrong. Not just a little wrong, but wrong by a factor of 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the entire history of science. This single number, if correct, would have blown the universe apart in its first moments of existence, preventing stars, galaxies, or life from ever forming. So the cosmological constant remains a profound puzzle, a compelling idea that fits the observation perfectly, yet clashes violently with our fundamental understanding of physics. Why is the energy of empty space so incredibly fine-tuned to allow for our existence? The search for an answer to that question leads us to theories that are even stranger. This staggering failure of prediction is why many physicists look beyond a simple cosmological constant. What if dark energy is not a fixed property of empty space, but something that evolves? This idea leads us to a theory known as quintessence. Imagine a new, invisible field that permeates all of space, a cosmic cousin to the Higgs field. Unlike the stubborn, unchanging cosmological constant, this quintessence field is dynamic. It can change in strength and density over time, and its repulsive push can vary. In its simplest form, this field would act like a fifth fundamental force, an energy fluid with negative pressure that stretches the fabric of the cosmos. The name itself is a deliberate callback to an ancient idea, Aristotle's fifth element, the pure substance that made up the heavens beyond the moon. This modern quintessence is proposed as the mysterious fifth element of our universe. One of the most compelling versions of this idea involves something called a tracker field. Think of a sophisticated thermostat in a vast cosmic building. A tracker field is designed to automatically adjust its energy density to match the dominant energy in the universe at any given era. In the early, dense universe, it would have lain dormant, overshadowed by radiation. Later, as matter spread out, it would have slowly awakened, its energy finally becoming dominant in the recent cosmic past to drive the accelerated expansion we see today. This elegant mechanism could solve the fine-tuning problem. Instead of requiring a miraculously precise initial value like the cosmological constant does, a tracker field naturally finds its way to the right energy level to drive acceleration, no matter where it started. It is a theory that offers a history, a story of change, rather than a single, static number. But if quintessence is real, its dynamic nature would leave a distinct fingerprint on the universe, subtly altering the rate of expansion in ways we could potentially measure. The race is on to find that signature, to see if the push of dark energy is truly constant, or if it has been slowly shifting for billions of years. What if our very understanding of gravity is the thing that is wrong? While most scientists hunt for an unseen substance, a radically different approach suggests we do not need dark matter at all. This is the core idea behind modified Newtonian dynamics, or MND. It proposes that Isaac Newton's famous laws, which work perfectly in our solar system, break down in the vast, sparse outskirts of galaxies where gravity is incredibly weak. In these regions of extremely low acceleration, gravity might behave differently, becoming slightly stronger than Newton or Einstein predicted. This extra gravitational kick would then hold fast-spinning galaxies together without any need for invisible dark matter halos. Think of it like this: you have a car that, according to the manual, should only be able to go 60 miles per hour. Yet on a long, empty highway, you find it can actually reach 80. Instead of inventing a mysterious new fuel in the gas tank to explain this, Mund suggests the manual itself is incomplete. The rules of how the engine performs change at very high speeds. In the cosmic case, the rules of gravity change at very low accelerations. The theory's greatest success is its stunning ability to predict the rotation speeds of many types of galaxies using a single new rule, without any fiddly adjustments for dark matter. For certain galaxies, especially isolated ones, Mund predictions match the observed rotations almost perfectly, something the standard dark matter model often struggles with unless it carefully tunes the distribution of the invisible stuff. But Mund is not a perfect solution. It faces its own monumental challenges. When we look at the largest scales in the universe, like colossal clusters of galaxies, the evidence for some form of unseen mass becomes overwhelming. The way these clusters bend light from distant objects, an effect called gravitational lensing, reveals far more gravity than Mund alone can typically explain. To account for this, proponents often have to suggest that some regular yet unseen matter is still present, blurring the clean elegance of the original idea. So we are left with a deep and unresolved conflict. Is the universe filled with a mysterious, invisible substance that governs the fate of galaxies? Or are we still missing a fundamental chapter in the book of gravity itself? This battle between dark matter and modified gravity forces us to question the bedrock of physics. Perhaps our universe is not a unique masterpiece, but a single page in an infinite cosmic library. This is the multiverse hypothesis, a concept that offers a startling answer to the fine-tuning of dark energy. In this framework, our universe is just one of countless bubbles in a vast cosmic foam, each with its own unique physical laws and constants. The energy density of our vacuum, the very strength of dark energy, would then not be a carefully chosen number, but simply a random roll of the dice in our particular cosmic neighborhood. We just happen to live in a bubble where this value is strangely small and perfect for life, a consequence of a selection effect rather than design. String theory, a leading candidate for a theory of everything, provides a mechanism for this. It suggests a landscape of possible vacuum states, a staggering 10 to the 500 different ways for a universe to exist. Each has a different value for the cosmological constant. In such an unimaginably vast landscape, it becomes almost inevitable that a few universes, purely by chance, would have the right conditions for stars, planets, and life to emerge. Our universe is one of those lucky ones, but this cosmic lottery comes with a terrifying potential receipt. What if our particular vacuum state is not perfectly stable? This leads to the theory of vacuum decay, one of the most existential threats conceivable. Our universe's vacuum might be metastable, like a ball resting in a small dip on the side of a vast, steep hill. It seems stable for now, but it is not in the lowest possible energy state. A true, stable vacuum would have a much lower energy. The horrifying prospect is that a random quantum event could trigger a transition, creating a microscopic bubble of this true vacuum. This bubble would then expand in all directions at nearly the speed of light. The laws of physics inside this bubble would be completely different. Atoms would not hold together, and the fundamental forces as we know them would cease to exist. The wall of this expanding bubble would be a wave of total cosmic annihilation, rewriting reality itself as it moves, leaving nothing recognizable in its wake. And because it moves at light speed, we would have no warning. One moment the universe is as it is, the next everything is gone. Is this a genuine threat or just theoretical speculation? The mathematics suggests our vacuum is likely metastable, but with a half-life so astronomically long that the probability of it happening within the entire observable universe is negligible. Yet, the mere possibility that the latent energy propping up our reality could suddenly be released, erasing the cosmos in a flash, adds a profound and unsettling dimension to the mystery of dark energy. But what if dark matter is not a flaw in our theories, but a hidden population of particles we simply have not detected yet? One of the most celebrated ideas in modern physics, supersymmetry, offers a compelling candidate. It proposes a profound and elegant symmetry in nature, where every known particle in the standard model has a hidden, super-heavy partner. The familiar electron would be paired with a theoretical selectron, quarks with squarks, and photons with photinos. This mathematical beauty solves several major puzzles in physics at once, but its most tantalizing gift might be the solution to the dark matter mystery. Within this new family of particles, the lightest supersymmetric particle, or LSP, is predicted to be completely stable. It would have been created in the fiery forge of the Big Bang and simply lingered, unable to decay into anything else because it is the lightest of its kind. The most popular candidate for this role is the neutralino, a heavy, neutral particle that barely interacts with ordinary matter. It would pass through you, your house, and the entire Earth as if they were not even there. This makes it a perfect example of a weakly interacting massive particle, a WIMP. Vast clouds of these invisible neutralinos could form the gravitational scaffolding of every galaxy, their collective mass creating the powerful pull that holds spinning stars in place without emitting a single photon of light. For decades, this has been the leading hypothesis, an elegant solution that ties together the quest for a deeper theory of particles with the cosmic need for dark matter. Yet, despite incredibly sensitive experiments designed to catch the rare recoil of a WIMP striking an atomic nucleus deep underground, these particles have stubbornly refused to appear. Their continued absence forces us to wonder if the answer is even more exotic than we ever imagined. The absence of WIMP has sent physicists digging deeper into the particle catalogue, and they have uncovered another fascinating candidate born from a completely different cosmic puzzle. This is the story of the action, a hypothetical particle so lightweight and ghostly it makes the neutralino seem almost bulky. Its origins lie not in the dark matter mystery itself, but in one of the most perplexing fine-tuning problems in all of physics, known as the strong CP problem. Inside the nucleus of an atom, the strong nuclear force holds quarks together to form protons and neutrons. The bizarre laws governing this force, described by a theory called quantum chromodynamics, seem to allow for a strange violation of symmetry between particles and their mirror images, a violation that would generate a permanent electric dipole moment for the neutron. Think of the neutron, a neutral particle having a tiny, inherent positive charge on one end and a negative charge on the other, like a microscopic battery. Yet, despite incredibly precise experiments, no such dipole moment has ever been found. The neutron is perfectly, symmetrically neutral to an astonishing degree of accuracy. This means that a certain fundamental parameter in the equations of nature, a number that could be any value, appears to be tuned to zero for no apparent reason. To explain this unnatural perfection, physicists proposed a new mechanism, a new field that would automatically cancel out this unwanted asymmetry. The quantum ripple of this field would be a new particle, the action. It was an elegant fix for a deep theoretical problem, but then scientists realized this same particle had all the right properties to be the dark matter. Actions would be incredibly light, potentially billions of times lighter than an electron, and they would be produced in copious amounts in the hot early universe. Most importantly, they are what we call cold dark matter, moving slowly and clumping together to form the gravitational seeds for galaxies. Because they interact so feebly with ordinary matter, a beam of actions could pass through a solid light year of lead without a single one being stopped. This makes them nearly impossible to detect, but not entirely. The most ambitious hunt for them is underway in experiments like the Action Dark Matter experiment, or ADMX. This machine is essentially a super-powered radio receiver, tuned to listen for the faintest signal in the universe. Inside a powerful magnet, the theory goes, an action from the dark matter halo of our galaxy could very rarely convert into a microwave photon. The ADMX experiment is designed to scan through millions of possible frequencies, listening patiently for the whisper of an action turning into a radio wave. It is a painstaking search for a ghost, a particle born to solve one profound mystery that may also hold the key to another, the invisible architecture of the cosmos itself. Our search for dark matter might be hiding in plain sight, embedded within one of the most common particles in the universe. You have likely heard of neutrinos, the ghostly subatomic particles that stream from the sun and pass through your body in their trillions every second. They are famously aloof, interacting with matter so rarely that they are notoriously difficult to detect. But what if there is an even more elusive version of these cosmic phantoms? This brings us to sterile neutrinos. Standard neutrinos are already strange. They come in 3 known types or flavors, and they only interact through gravity and the weak nuclear force, the force responsible for certain types of radioactive decay. Sterile neutrinos are a proposed 4th flavor, a shadowy cousin that takes this reclusiveness to an extreme. The sterile neutrino, as its name implies, would not interact via the weak force at all. Its only connection to our world would be through the feeble tug of gravity. This makes it a perfect candidate for a component of dark matter, a particle that is truly, fundamentally dark. But how could such a particle be detected if it does not interact? The key might lie in a bizarre quantum phenomenon known as neutrino oscillation. We know that the 3 standard neutrinos can morph into one another as they travel through space. A neutrino born as an electron neutrino might be detected later as a tau neutrino. Certain anomalies in these oscillation patterns, measurements that do not quite match our predictions, could be explained if the known neutrinos were occasionally oscillating into this 4th sterile state, a particle that then vanishes from our detection entirely. If sterile neutrinos are real, they would represent a form of warm dark matter. This is a crucial distinction. Cold dark matter, like WIMP or actions, moves slowly and is excellent at clumping together to form the smallest structures like the cores of galaxies. Hot dark matter, like standard neutrinos, moves at near light speed and tends to smooth everything out, preventing small clumps from forming. Warm dark matter is a middle ground. Sterile neutrinos would be heavier and slower than their standard relatives, but still more energetic than cold dark matter candidates. This unique property would leave a specific imprint on the cosmos. A universe with warm dark matter would have fewer small, dwarf galaxies orbiting large ones than a universe with cold dark matter. The distribution of galaxies on the largest scales would have a subtly different texture. Astronomers are now looking for exactly this signature, searching the cosmic map for hints that the dark matter was, at least in part, a bit warmer than we once thought. The sterile neutrino remains a ghost within a ghost, a hypothetical solution to two puzzles at once, potentially explaining the odd behavior of known neutrinos while quietly shaping the vast architecture of the universe. While sterile neutrinos are ghosts of the particle world, another theory suggests the dark matter could be made of cosmic monsters. Black holes are typically born from the violent deaths of massive stars, but what if a vast number of them were forged in the furnace of the Big Bang itself? These would be primordial black holes, not born from stars, but from the intense density fluctuations in the first moments of the universe. Imagine the newborn cosmos as a pot of water coming to a rapid boil, with tiny regions of space so dense and hot that they simply collapse directly into black holes. These ancient objects could range in size from smaller than an atom to many times the mass of our Sun, and they would be made of pure, crushed space-time, completely dark and invisible. For decades, this idea was on the fringes, as observations seemed to rule out primordial black holes making up all the dark matter. If there were enough asteroid mass black holes to account for the missing gravity, they would frequently pass in front of stars, causing a noticeable flicker in their light, an effect called gravitational microlensing. Surveys looking for these flickers largely came up empty, suggesting these small black holes could not be the dominant form of dark matter. The case appeared closed until a cosmic echo changed everything. The first direct detection of gravitational waves by LIGO in 2015, ripples in space-time from two massive black holes colliding over 1 billion light-years away, sent a shockwave through the astrophysics community. The black holes involved were surprisingly heavy, each around 30 times the mass of the Sun. How did such large black holes form? One compelling explanation is that they were not the products of dead stars, but ancient primordial black holes from the dawn of time. This revelation reopened the case entirely. If a vast population of these mid-sized black holes exists, floating silently in the dark halos of galaxies, they could constitute a significant portion, if not all, of the dark matter. The search has now shifted. Astronomers are no longer just looking for the tiny flickers of small black holes, but for the subtle ways these larger, ancient ones reveal themselves. They might cause stars to slightly magnify and brighten as they pass by, a longer, gentler microlensing event. They could even capture stray clouds of gas, creating a faint, telltale glow before devouring them. The hunt is on for these primordial relics. The possibility that the invisible glue holding galaxies together is a hidden population of the universe's most extreme objects, a cosmic secret hiding in plain sight for over 13 billion years. Perhaps the most radical rethinking of reality itself comes from the holographic principle. This idea suggests that our three-dimensional universe, with all its depth and volume, might be a projection from a two-dimensional surface, much like a hologram emerges from a flat piece of film. The theory finds its roots in the strange physics of black holes. When an object falls into a black hole, what happens to all the information it contained? The laws of quantum mechanics insist that information can never be truly destroyed. Yet a black hole's event horizon seems to be the ultimate one-way street. Physicists wrestling with this paradox discovered something astonishing. They found that the maximum amount of information a region of space can contain is not proportional to its volume, but to the surface area of its boundary. Think of a sphere. You would expect the information content to be related to the space inside it, the volume. but this principle says the real information limit is set by the area of the sphere's surface. It is as if all the events happening in your room, every particle interaction and force, are not truly happening in the room itself, but are encoded on the walls, ceiling, and floor. Your perception of a three-dimensional world is a magnificent illusion decoded from a cosmic flat screen. This leads to a profound implication for gravity and the universe's missing energy. In this framework, gravity is no longer a fundamental force like the others. Instead, it emerges from the quantum interactions happening on that distant two-dimensional boundary. The dark energy driving cosmic acceleration could then be a consequence of this deeper, holographic coding. The energy budget of the cosmos would not be a simple sum of its parts, but a complex result of information processing at its edges. We are not just in the universe, we may be an image of it, a projection whose source code is written on the farthest horizon of space. What if dark matter and dark energy are not two separate mysteries, but different faces of the same cosmic entity? This is the core idea behind the Chaplygin gas, a single, exotic fluid proposed to account for the entire missing 95% of the universe. The name comes from a mathematical model developed over a century ago by a Russian physicist, Sergei Chaplygin, to describe the aerodynamics of certain fluids. In the cosmic context, this model describes a substance with a truly bizarre property. Its pressure is negative, and it becomes harder to compress the more you try to push on it. Imagine trying to squeeze a balloon filled with an otherworldly gel. The more force you apply, the more it pushes back, resisting you with an increasing spring-like force. In the early, dense universe, this Chaplygin gas would have behaved just like cold, dark matter. Its particles would have clumped together under gravity, providing the scaffolding for the first galaxies to form. But as the universe expanded and thinned out, this same fluid would have undergone a dramatic transformation. Its negative pressure would have begun to dominate, creating a repulsive force that drives galaxies apart, behaving exactly like the dark energy we observe today. It is a cosmic two-in-one solution, an elegant unification that simplifies the universe's biggest puzzle. One of the most popular versions of this idea is known as the generalized Chaplygin gas. This model gives the fluid more flexibility, allowing it to transition more smoothly from its dark matter phase to its dark energy phase across cosmic history. Theoretically, it is a beautiful idea, but does it match what we actually see in the sky? The first major test comes from observations of distant supernovae. These stellar explosions act as cosmic mile markers, allowing us to measure the expansion history of the universe. The data shows a very specific acceleration profile, and the Chaplygin gas model must fit this curve perfectly to remain viable. While it can be tuned to match the supernova data reasonably well, it often struggles to simultaneously explain the subtle patterns imprinted on the cosmic microwave background, the afterglow of the Big Bang. The precise peaks and valleys in this ancient light tell a detailed story of the universe's early composition and geometry, a story that often seems to prefer the standard model where dark matter and dark energy are distinct components. The Chaplygin gas, for all its elegance, often finds itself caught between these two powerful sets of observations, unable to fully satisfy both without introducing complications. It remains a fascinating and provocative idea, a reminder that the simplest solutions are not always the ones nature chooses. Could the universe's dark side be a single, shape-shifting substance, or are we truly dealing with two separate, fundamental unknowns? String theory paints a picture of reality far stranger than our three-dimensional experience suggests. It proposes that the fundamental ingredients of the cosmos are not point-like particles, but tiny, vibrating strings. And for this mathematics to work, the universe must have more than the three spatial dimensions we know. There could be 6 or 7 extra dimensions, all curled up into a space so infinitesimally small we never perceive them. Brain cosmology takes this wild idea and runs even further with it. In this framework, our entire universe, with all its galaxies, stars, and planets, is a three-dimensional membrane, or brain for short, floating within a higher dimensional reality known as the bulk. Everything we know and are made of, all the matter and forces except for one, is stuck to this brain like images painted on a soap bubble. The one force that is different, the one that can leak across dimensions, is gravity. This could be why gravity is so astronomically weaker than the other fundamental forces. A magnet the size of a coin can lift a paperclip, defeating the gravitational pull of the entire Earth. In the brain world picture, gravity appears weak to us because its lines of force are not confined to our brain. They spread out or leak into the vastness of the bulk, diluting their strength from our three-dimensional perspective. This elegantly solves the so-called hierarchy problem, the puzzling question of why gravity is so feebly weak compared to the other forces. But what does this have to do with dark energy? The energy of empty space, the driver of cosmic acceleration, could be a direct result of our brain's existence and its dynamics within the bulk. One compelling theory suggests that another brain, a parallel universe, could be floating in the bulk a microscopic distance away from our own in these extra dimensions. The invisible energy of the vacuum, the force pushing our universe apart, could be the subtle gravitational tug from this neighboring world, a cosmic shadow we can never directly see. Another, even more dramatic possibility is that dark energy is a remnant of a primordial collision. Our brain and another one could have slammed together in the distant past, flooding our universe with a burst of repulsive energy that initiated the period of accelerated expansion we see today. This cyclical model of colliding brains has even been proposed as a possible alternative to the Big Bang, a cosmic reset button that happens over and over again for eternity. The beauty of brain cosmology is its sheer audacity, suggesting that the greatest mysteries of our cosmos are not about what is inside our universe, but about where our universe itself resides. The search for dark energy then becomes a probe into the very architecture of reality, a quest to feel the subtle pull of worlds we can never visit. This phantom energy model takes the acceleration of the cosmos to its most terrifying logical extreme. While the standard cosmological constant represents a steady, relentless push, phantom energy is an unstable feedback loop of repulsion. Its defining feature is an equation of state where the pressure is so profoundly negative that it causes the energy density of the vacuum to actually grow as the universe expands. Think of it as a cosmic engine that becomes more powerful the more space it creates, a runaway force with no built-in brakes. The ultimate consequence of this ever-increasing push is a cosmic doomsday scenario known as the Big Rip. Imagine the expansion of space itself accelerating not just steadily, but at an exponentially increasing rate. For billions of years, the effects would be subtle. The first casualty would be the cosmic large-scale structure. The gravitational glue holding clusters of galaxies together would be overwhelmed, and these vast cities of stars would be flung apart into the void. Next, individual galaxies would be torn asunder. The Milky Way would be shredded, its stars scattered like dust in a hurricane. As the end draws near, the relentless stretching of space would overcome the forces holding individual solar systems together. Planets would be ripped from their stars. Then, the expansion would target the stars and planets themselves. The nuclear forces binding a star together would be no match for the phantom energy. Every sun, every world would be violently pulled apart. In the final, horrifying moments, even the fabric of space-time and the atoms that make up all matter would be subjected to this ultimate force. Atomic nuclei would be torn from electrons, and the quarks within protons and neutrons would be separated. Reality itself would be dissolved into a thin, cold mist of disconnected fundamental particles, unable to ever interact again. The universe would not end with a collapse or a freeze, but with a catastrophic shredding of every structure, large and small. Is this our future? Current observational data suggests that if dark energy is of the phantom type, its ferocity is still very mild, pushing the potential big rip trillions of years into the future if it happens at all. Yet the mere possibility that the vacuum of space could harbor such a self-amplifying destructive force forces us to confront a profound question. Is the dark energy we observe today a gentle, constant pressure, or is it the first whisper of a coming storm that will eventually unravel the cosmos? Gravity may not be a fundamental force at all, but a side effect, an illusion born from the chaotic dance of information. This revolutionary idea, known as emergent gravity, was proposed by physicist Eric Verland, and it suggests we have been thinking about the cosmos backwards. Instead of gravity being a primary ingredient that tells matter how to move, Verland argues it emerges from something more basic, the quantum entanglement of countless microscopic bits of information woven into the fabric of space-time. Think of the temperature in a room. You can feel it as a real, tangible property, but it is not a fundamental entity. It emerges from the frantic, collective motion of trillions of invisible air molecules. In the same way, gravity could be a thermodynamic consequence, a kind of elastic response of space itself when it is filled with matter and energy. The mathematics behind this is profound, drawing a direct link between the laws of gravity and the laws of thermodynamics, the science of heat and energy flow. So what does this have to do with dark matter? Verland's theory makes a stunning prediction. When you apply his equations to the environment inside a galaxy, the collective quantum entanglement of space naturally generates an extra gravitational effect. This additional pull is not caused by an invisible halo of particles, but by the way the dark energy in the universe's vacuum reacts to the presence of ordinary matter. It is as if the empty space within a galaxy, stirred by the stars and gas, becomes stiffer, more resistant, and this resistance manifests as an extra attractive force. This emergent gravity naturally reproduces the exact same rotation curves that astronomers observe in spiral galaxies, the very same data that first demanded the existence of dark matter. The stars at the edges of galaxies move too fast for the visible matter alone, but according to this idea, it is because we were not accounting for the gravitational contribution of the universe's dark energy itself, activated by the galactic environment. The theory elegantly does away with the need for a mysterious, undiscovered particle. Yet, this radical proposal faces its own significant challenges. While it works remarkably well for isolated galaxies, it struggles to explain the gravitational lensing we see in colossal clusters of galaxies, where the bending of light is so extreme that it seems to require more concentrated, particle-like dark matter to account for it. The battle is far from over, but emergent gravity forces a fundamental question. Are we hunting for a ghostly substance, or are we on the verge of realizing that gravity itself is a cosmic mirage, a story told by the hidden information that constructs our reality? The quest to unify the cosmos has long been physics' ultimate goal, a dream of a single, elegant framework that can describe everything from the dance of galaxies to the flutter of a quantum particle. This grand ambition is known as the theory of everything, and its potential to solve the dark energy riddle is immense. At its heart lies the century-old conflict between our two most powerful descriptions of reality. General relativity paints a beautiful, continuous picture of space and time as a flexible fabric, perfectly explaining gravity on cosmic scales. Quantum mechanics, in stark contrast, reveals a jittery, probabilistic world where particles pop in and out of existence and fields constantly fluctuate. Both theories are spectacularly successful in their own domains, but they are fundamentally, violently incompatible. When you try to apply the equations of general relativity to the tiny quantum scale, or when you try to stuff the immense gravity of a black hole into a quantum box, the math simply breaks down, producing nonsensical infinities. This schism is not just a technicality, it is a gaping hole in our understanding, and it sits right at the center of the dark energy problem. Remember that catastrophic mismatch in the predicted energy of the vacuum. That unfathomable number, 1 followed by 120 zeros too large, is the direct result of our inability to reconcile gravity with quantum physics. We are trying to calculate the energy of empty space using quantum tools, but without a quantum theory of gravity to tell us how spacetime itself reacts to that energy, the result is meaningless. A true theory of everything would finally provide the rules for this interaction, showing us how the frenetic quantum activity of the vacuum and the smooth geometry of spacetime talk to one another. It could reveal that these two descriptions are merely different perspectives on a single, deeper reality, and in doing so, it might naturally resolve the cosmological constant problem. The vacuum energy we measure might not be a raw, fundamental value, but a net result, the leftover from a complex cancellation between countless quantum contributions. One promising path toward this unification is loop quantum gravity. This approach takes general relativity and quantizes it, suggesting that space itself is not a smooth continuum, but is woven from a fabric of tiny, finite loops. Think of the fabric of your shirt. From a distance, it looks perfectly smooth and continuous, but up close, you see it is made of individual, interwoven threads. Loop quantum gravity proposes that spacetime has a similar granular structure at the smallest possible scale, the Planck length. This fundamental graininess could impose a natural limit, preventing the wild quantum fluctuations from contributing infinite energy to the vacuum. By discretizing space, it might provide a natural cutoff, taming the calculation and bringing the theoretical prediction of dark energy in line with the tiny value we observe. The hope is that a complete theory of everything would not need to explain why the vacuum energy is so small, but would instead show that it could not be any other way, that its value is a necessary and fixed output of a unified cosmos. The constants of nature we measure, like the strength of dark energy, might not be arbitrary numbers plugged into our equations, but the inevitable consequences of a single underlying principle. Unlocking this principle would be the final step in a journey that began with Einstein, revealing that the universe's greatest mystery was never a missing substance, but a missing chapter in the story of physics itself. This selection effect is known as the anthropic principle, a concept as unsettling as it is compelling. It argues that the universe we observe must be compatible with the existence of conscious life to be observed at all. We are not discovering the fundamental laws of a unique cosmos, but simply inhabiting one of the rare corners of a multiverse where the numbers add up correctly. The value of dark energy is the ultimate example. If it were just a little bit stronger, the repulsive force would have torn apart the primordial clouds of gas before they could ever collapse into the first stars and galaxies. The universe would be a vast, empty, and ever-accelerating void, with no planets and no one to wonder about its origins. If dark energy were slightly weaker, the inward pull of gravity would have reversed the expansion long ago, causing a catastrophic big crunch that would have snuffed out any potential for life billions of years ago. Our existence, therefore, places a tight constraint on the possible values this cosmic constant can take. We find ourselves in a universe with a curiously small, but not zero, amount of dark energy, a narrow window that permits billions of years of cosmic evolution and the eventual rise of observers. This is not evidence of design, but of a cosmic lottery with an almost infinite number of losing tickets. String theory's landscape of possible universes provides the mechanism for this lottery. With its 10 to the 500 possible vacuum states, it guarantees that a tiny fraction of universes will, by pure chance, have the minuscule value of dark energy we observe. In this vast ensemble, it becomes statistically inevitable that a few universes will be bio-friendly. The profound fine-tuning we measure is then demoted from a deep mystery to a local condition, a simple consequence of our own existence. Yet this explanation leaves many scientists deeply unsatisfied. It feels like a retreat from the classic scientific goal of explaining why the laws of nature are what they are. Instead of a causal explanation, the anthropic principle offers a post hoc justification. It tells us we are lucky, but it does not tell us why this particular form of luck is even possible. The debate forces a fundamental question about the nature of science itself. Are we seeking a unique, predictive theory of everything, or are we merely cosmic cartographers, mapping the island we happen to inhabit in an infinite archipelago of realities? But what if the very rules of the game have been changing all along? The bedrock of physics rests on fundamental constants, numbers like the speed of light and the strength of gravity, which we assume are fixed and unchanging. Yet, a radical theory suggests these pillars of reality might be slowly shifting over cosmic time, and this drift could be the true source of the force we call dark energy. Imagine the gravitational constant, which dictates the pull between all masses, was slightly stronger in the distant past. A more powerful gravity in the early universe would have forged the first stars and galaxies more quickly, altering the timeline of cosmic evolution. As this constant weakened over billions of years, its diminishing grip could create the illusion of a new repulsive force taking over, mimicking the accelerated expansion we observe without any dark energy at all. The same logic applies to other constants, like the fine structure constant, which governs the strength of electromagnetic interactions. If light and matter interacted differently long ago, the entire cosmic distance ladder we use to measure expansion, built on the predictable brightness of supernova, could be giving us a distorted picture. How could we possibly test such a mind-bending idea? The universe has left us a natural laboratory in the distant cosmos. When astronomers point their telescopes at incredibly bright quasars, the light from these beacons has traveled for billions of years to reach us. On its journey, it passes through vast clouds of interstellar gas, which absorb specific wavelengths of light, creating a unique barcode of dark lines in the spectrum. By analyzing these ancient absorption lines with incredibly precise instruments, scientists can check if the fine structure constant has changed. A shift in the spacing of these lines would be a direct signal that the laws of physics are not eternally fixed. Another crucial test comes from the cosmic microwave background. The precise patterns in this afterglow are a frozen snapshot of the universe's infant geometry, sensitive to the exact strength of gravity and other forces in its first moments. Any significant variation in the fundamental constants would leave a distinct, and so far undetected, fingerprint on this radiation. While current evidence suggests any such changes are extraordinarily small, the search continues with ever more sensitive probes. This theory challenges our deepest assumptions, proposing that the mystery of dark energy is not a substance, but a symptom, a clue that the fundamental nature of reality itself is fluid and evolving. Perhaps the Big Bang was not a singular beginning, but a violent rebirth. The ekpyrotic universe model offers this radical alternative, proposing our cosmos was born from a spectacular collision in a higher dimensional reality. The name itself comes from the Greek word for conflagration or fire, a fitting title for a genesis born of immense force. In this brain world scenario, our three-dimensional universe exists on one membrane, while a parallel universe exists on another, both floating like immense, invisible sheets in a hidden dimension. For most of cosmic history, these branes are separate and cold, but they are drawn together by a faint force across the bulk. When they finally collide, the impact releases an unimaginable amount of energy, flooding our brain with radiation and matter and igniting what we perceive as the hot Big Bang. This event was not the creation of space and time from nothing, but a transformation, a reset of a pre-existing cosmos. This elegant idea naturally solves two of the biggest puzzles in standard cosmology. The first is the flatness problem. Our universe is remarkably flat on large scales, meaning its geometry follows the rules of Euclid, a condition that requires an incredibly precise balance of energy and expansion in the first moments. In the standard model, this requires unnatural fine-tuning, but in the ekpyrotic scenario, the violent collision and subsequent expansion naturally smooth and flatten the brain, like ironing out the wrinkles on a vast sheet. The second puzzle is the horizon problem. Distant regions of the cosmos have the same temperature and properties, even though they have never been in causal contact, as if two strangers on opposite sides of the world were wearing the exact same outfit. The standard theory explains this with a brief period of hyper-expansion called inflation. The ekpyrotic model offers a different solution. Before the collision, the two brains were very close and could exchange energy, allowing the entire volume to reach a uniform temperature. The collision and subsequent expansion then preserved that uniformity, explaining the matching conditions without the need for inflation. But what does this have to do with dark energy? This is where the model becomes cyclic. The initial collision that created our universe is not a one-time event. After the bang, our universe expands and evolves, with galaxies forming and dark energy eventually taking over, driving an accelerated expansion that stretches the cosmos thin and cold over trillions of years. But this very expansion is what sets the stage for the next cycle. As the brain becomes empty and uniform, the subtle attractive force between brains can once again draw them together, leading to another collision and another fiery rebirth. In this breathtaking vision, dark energy is not a force of ultimate destruction, but a crucial cosmic cleanser. It is the mechanism that dilutes the universe, wiping the slate clean and preparing the stage for the next great collision. The acceleration we measure today is not a one-way ticket to a cold, dark future, but merely the prelude to a new beginning. We are living in the quiet, expanding phase between two cosmic conflagrations, part of an eternal cycle of birth, death, and rebirth that has played out countless times before. This model reframes our entire cosmic story, suggesting that the greatest mysteries of our universe are not about its origin, but about its place in an infinite cyclical drama. A universe with two separate dark components feels unnecessarily complex. What if a single, strange substance could wear both masks? This is the promise of the dark fluid theory, a concept that proposes a unified cosmic liquid with a property so bizarre it seems impossible: negative mass. Imagine a substance that, when pushed, accelerates toward you instead of away. This is not mere science fiction. It is a serious, though speculative, solution to the twin mysteries of dark matter and dark energy. In this model, the dark fluid possesses a negative gravitational mass. This means it would react to gravity in the opposite way of everything else we know. Ordinary matter with positive mass is always attracted to other positive masses, but this dark fluid would be gravitationally repelled by positive matter. It would flee from galaxies and clusters, creating a kind of negative pressure halo around them. Now consider the implications within a galaxy. The dark fluid, repelled by the galaxy's core of positive matter, would not collapse into a tight sphere. Instead, it would form a vast, diffuse halo, exactly where we inferred dark matter must be. Its presence would still exert a gravitational pull on the outer stars, explaining their high rotation speeds without requiring a cloud of invisible particles. The fluid's distribution naturally matches the dark matter profile we observe. Now, zoom out to the scale of the entire cosmos. As the universe expands, this repulsive nature of the dark fluid takes on a new role. Its negative mass means it generates a repulsive gravitational field on cosmic scales, a persistent push that drives galaxies apart at an accelerating rate. In this single framework, the dark fluid acts as a clumpy, gravitationally attractive halo within galaxies, and a smooth, repulsive energy in the vast intergalactic voids. It is one entity, one answer to two questions. However, this elegant idea faces immense physical and mathematical challenges. The concept of negative mass is notoriously difficult to square with our established theories of gravity. In many models, such a fluid would be catastrophically unstable, leading to runaway motions where particles endlessly accelerate, gaining infinite energy and momentum, which clearly does not happen in our stable universe. Proponents work to build mathematical formulations that avoid these instabilities, but it remains a significant hurdle. Furthermore, making a unified dark fluid compatible with the precise snapshot of the early universe provided by the cosmic microwave background is a formidable task. The intricate patterns in that ancient light tell a very specific story about how matter clumped together to form the first seeds of structure. A single dark fluid must be able to reproduce all those subtle peaks and valleys as perfectly as the standard two-component model, a benchmark it has yet to definitively meet. The dark fluid theory dares to ask if our cosmic inventory is simpler than we think, challenging us to consider whether the universe's greatest secrets are woven from a single, shadowy thread. The quantum vacuum is far from empty. It crackles with a hidden energy, a seething sea of virtual particles that blink in and out of existence in a relentless quantum dance. We can actually witness this phenomenon in a laboratory through a remarkable effect named after the Dutch physicist who predicted it. The Casimir effect places two uncharged, perfectly smooth metal plates incredibly close together in a vacuum. At this microscopic scale, the chaotic froth of virtual particles is subtly restricted. Only certain wavelengths of these quantum fluctuations can fit between the plates, while a greater variety can exist outside them. This creates a pressure imbalance, with more virtual particles pushing on the outside of the plates than on the inside. The result is not an explosion, but a gentle, irresistible force that pulls the two plates together. It is a direct, measurable proof that empty space has a palpable energy. This energy of the vacuum, known as zero-point energy, is not just a fleeting curiosity. It is the very energy that, when plugged into Einstein's equations as the cosmological constant, should be driving the expansion of the universe. This is where the mystery deepens into one of physics' greatest embarrassments. When we calculate the total zero-point energy of all these quantum fields in empty space, the number we get is monstrous. It suggests a vacuum energy density so immense that it should have ripped the fabric of space-time apart in the first instant of the Big Bang. The universe as we know it, with its delicate galaxies and complex chemistry, would have been utterly impossible. Yet, when we look at the actual cosmos and measure the strength of dark energy from the acceleration of galaxies, the value is almost nothing. It is staggeringly small, a tiny whisper of a force when our theories predict a deafening roar. The discrepancy is not a small error. It is a factor of 1 with 120 zeros after it. To grasp the scale of this miscalculation, imagine predicting that a single breath of air would contain more mass than the entire observable universe. The number is so catastrophically wrong that it represents a fundamental crisis in our understanding. This colossal mismatch between quantum field theory and cosmological observation is the cosmological constant problem. It tells us that something is profoundly missing from our picture. Either our understanding of the quantum vacuum is incomplete in some crucial way, or a mysterious cancellation mechanism is at work, perfectly neutralizing almost all of this vacuum energy and leaving behind only the faintest residue we call dark energy. Why does the hum of empty space not tear our reality to shreds? The answer to that question may lie in a deeper layer of physics, a theory that finally unites the quantum world with the force of gravity. Einstein's theory of general relativity has passed every test we have thrown at it for over a century, but its reign may not be absolute. A class of theories known as F of R gravity proposes a subtle but profound tweak to the master's equations. In Einstein's original work, the curvature of spacetime is described by a specific mathematical term, the Ricci scalar, represented by the letter r. F of r gravity suggests that gravity's behavior is not governed by this simple r, but by a more complex function of r, hence the name. This function acts like a filter, amplifying or suppressing gravity's pull under certain cosmic conditions. The goal is to explain both the rapid orbits of stars in galaxies and the accelerating expansion of the universe using only modified gravity, eliminating the need for both dark matter and dark energy in one stroke. Imagine the force of gravity as a spring. In our solar system, where matter is dense, the spring is stiff and behaves exactly as Newton and Einstein predicted. But in the vast, sparse outskirts of a galaxy, the same spring could become more elastic, providing a stronger pull over long distances than expected. This would explain why stars on the edges of galaxies orbit so quickly without any dark matter halo. On cosmic scales, this modified spring could also produce a repulsive effect, mimicking dark energy by driving galaxies apart. These theories are not just mathematical curiosities, they make specific, testable predictions. One key prediction involves the behavior of light. When light from a distant galaxy is bent by the gravity of a foreground cluster, an effect called gravitational lensing, F of r gravity predicts a specific relationship between the amount of bending we see and the mass of the visible matter. It suggests that the bending should be more pronounced for a given amount of starlight than in standard gravity. This gives astronomers a direct way to test the theory against the dark matter model. So far, the evidence is mixed. Observations of some galaxy clusters seem to align better with the presence of dark matter, while studies of individual galaxies sometimes lean toward the modified gravity explanation. Another critical test comes from our own cosmic backyard. The precise orbits of spacecraft around Earth and the gravitational dynamics within our solar system are exquisitely measured. Any modification to gravity must leave these local motions completely untouched, preserving all of Einstein's successful predictions here while only changing the rules in the extremely weak gravity of interstellar space. This is a very tight constraint, forcing the F of r function to be almost imperceptible in regions of strong gravity, yet significant in the void. The battle is far from decided, and it forces a fundamental question upon us. Are we on the verge of a new chapter in physics, one where we finally understand that gravity itself has different faces in different places? Or will Einstein's original vision, supplemented by invisible components, continue to rule the cosmos? Our reality might be just one thread in an infinite tapestry of parallel worlds. This is the many worlds interpretation of quantum mechanics, a vision where every possible outcome of a quantum event actually occurs, splitting our timeline into countless branching realities. While it sounds like science fiction, this idea offers a radical new perspective on the fine-tuning of dark energy. In the quantum realm, a particle exists in a blur of possibilities, a superposition of states, until an observation forces it to choose a single path. The many worlds interpretation argues it never actually chooses. Instead, the entire universe splits, with one version where the particle goes left and another where it goes right. Every decision, every random quantum event spawns new universes in an ever-expanding multiverse. So how could this endless branching affect the vacuum energy in our own cosmic branch? One speculative idea involves quantum decoherence, the process that makes quantum probabilities resolve into the definite reality we experience. Perhaps the specific value of our cosmological constant is not a fixed number, but a result of our universe continually decohering from the quantum soup of possibilities. The incredibly small value of dark energy we observe could be the most stable, classical outcome that emerges from this constant process of quantum selection. It is not fine-tuned, it is simply the most persistent state that can sustain a long-lasting universe like our own. An even more mind-bending proposal suggests that the parallel universes themselves are not entirely separate. Though we cannot travel to them, the ghostly influence of quantum mechanics might allow for subtle interactions across the multiverse. The vacuum of space in our universe could be subtly entangled with the vacuums of countless other worlds. The repulsive force we call dark energy might then be a residual pressure, a quantum echo from the collective energy of all those other realities pushing against the fabric of our own. In this view, the cosmological constant is not a property of our universe alone, but a reading of our place within an infinite ensemble. The vacuum energy is set by a cosmic average, a statistical outcome across a near infinity of branches, which naturally explains why it appears so small and finely tuned from our limited perspective. We are not special, we are simply typical within an unimaginably vast quantum landscape. This speculative bridge between the smallest quantum events and the largest cosmic mysteries challenges our very definition of reality, suggesting that the missing energy of the universe might be hiding in plain sight, distributed across the endless reflections of existence. A fifth dimension is not a modern idea, but a century-old one that aimed to unify the cosmos. In 1919, German mathematician Theodor Kaluza made a breathtaking discovery. He took Einstein's equations of general relativity, which describe gravity in 4 dimensions, and rewrote them for a universe with one extra spatial dimension. When he did this, something miraculous happened. Einstein's equations for gravity remained, but a new, separate set of equations appeared, perfectly describing James Clerk Maxwell's theory of electromagnetism. It was as if gravity and light were 2 different melodies played on the same 5-dimensional instrument. This was Kaluza-Klein theory, a stunningly elegant vision of unification. But where is this 5th dimension? Why do we not see it? The answer, provided by Swedish physicist Oskar Klein, is that it is curled up into a loop so infinitesimally small that it is completely hidden from our perception. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink yourself to the size of an ant, you would discover its circular surface, a second dimension you never knew was there. Kaluza and Klein proposed that our entire universe has a similar microscopic structure, with a tiny, circular dimension coiled around every single point in space. This elegant idea was largely shelved for decades, but it has experienced a dramatic revival in modern physics, particularly in string theory. If one extra dimension can unify gravity and electromagnetism, what could 7 more do? Modern extensions of this concept suggest that the dark energy accelerating our universe could be a direct consequence of the geometry and dynamics of these hidden dimensions. The energy we perceive as a mysterious repulsive force might simply be the gravitational pull from objects or forces operating in these extra dimensions, leaking into our own. Furthermore, these coiled-up dimensions could provide a natural home for dark matter. Certain vibrational patterns of the fundamental strings in these theories, or even whole particles that are free to move within the compact dimensions, could be completely invisible to us, yet they would possess mass and exert a gravitational pull. These Kaluza-Klein particles would be stable, massive, and only interact with our world through gravity, ticking every box for a dark matter candidate. The universe's greatest mysteries might not be missing from our reality at all, but simply operating on a dimensional frequency we are not built to perceive. Black holes are not just cosmic vacuums, they are profound puzzles that challenge the very nature of reality. At their heart lies the information paradox, a conflict between general relativity and quantum mechanics that Stephen Hawking famously uncovered. Hawking showed that black holes are not truly black, they slowly emit radiation and evaporate over astronomical timescales. But according to quantum law, information cannot be destroyed, it must be preserved. So when a black hole evaporates completely, what happens to all the information about every star, planet, and atom that ever fell in? Does it just vanish, violating a cornerstone of physics? Jacob Bekenstein and Hawking proposed a stunning answer that a black hole's entropy, its intrinsic disorder, is not stored within its volume but is encoded on its surface area, specifically on the event horizon. This Bekenstein-Hawking entropy suggests that the maximum information any region of space can hold is proportional to the area of its boundary, not the volume it contains. It is a radical hint that our three-dimensional world might be a projection from a two-dimensional surface. This deep connection between information, gravity, and thermodynamics forces us to reconsider the very nature of the vacuum. The seething quantum foam of virtual particles, which gives rise to Hawking radiation, is the same vacuum energy we call dark energy. The incredibly small value of the cosmological constant, the energy of empty space that drives cosmic acceleration, might be directly tied to how information is stored and processed at the most fundamental level of spacetime. Solving the information paradox could reveal that the universe's missing energy is not a substance at all, but a dynamic property of spacetime itself, a consequence of how information is woven into the fabric of reality. The key to the cosmos might not be a hidden particle, but a fundamental limit on how much data space can hold. What if the key to cosmic acceleration is a substance that breaks the ultimate speed limit? This is the radical proposal of tachyonic fields, a concept that dares to imagine particles that are born traveling faster than light. The name comes from the Greek word tachys, meaning swift, and these hypothetical entities would live their entire existence on the other side of light speed. According to our current understanding of physics, this is impossible, as Einstein's theory of relativity suggests that accelerating any object with mass to the speed of light would require infinite energy. Tachyons flip this logic entirely. They are theorized to have what is called an imaginary mass, a mathematical construct that means they cannot slow down to the speed of light or below. For them, light speed is not a barrier to break through, but a floor they can never fall below. So how could something that moves faster than light be responsible for the dark energy that stretches the very fabric of space? The connection lies in the strange properties such a field would possess. A tachyonic field permeating all of space would have a negative energy density and an equation of state with a powerful negative pressure. This is precisely the kind of repulsive gravity needed to drive the universe apart at an ever-increasing rate. In some theoretical models, this field could act like a cosmic instigator, its superluminal nature allowing it to influence vast regions of space almost instantaneously, seeding the uniform acceleration we observe across the cosmos. However, this idea is fraught with monumental theoretical hurdles. The existence of tachyons would seemingly violate causality, the fundamental principle that cause must always precede effect. If a tachyon could carry information, it could, in theory, arrive at a destination before it left its source, potentially creating paradoxes where an event could prevent its own cause. Furthermore, a universe filled with a background tachyonic field might be catastrophically unstable, prone to runaway production of particles that could drain energy from the vacuum in unpredictable ways. For now, tachyonic fields remain a fascinating but speculative corner of theoretical physics, a reminder that the solution to the dark energy puzzle might require us to rewrite not just our theories of matter, but our deepest understanding of time and causation itself. Even the most elegant theories must obey the universe's ironclad rules. One such rule, emerging from the depths of string theory, is the weak gravity conjecture. It makes a deceptively simple claim: in any universe that can support stable structures like atoms and planets, gravity must be the weakest of all forces. This is not just an observation about our world, it is proposed as a fundamental requirement for a consistent theory of quantum gravity. Think of the forces as a team of animals pulling a cart. Electromagnetism and the nuclear forces are the powerful horses, while gravity is a tiny, persistent mouse. The conjecture insists that for the cart of reality to hold together, the mouse cannot suddenly become a lion. This principle has a profound and very specific implication for the vacuum of space and the puzzle of dark energy. It suggests that our universe cannot be trapped in a false vacuum state for an arbitrarily long time. If the vacuum energy were too stable and its value did not decay, it could effectively create a situation where gravity was no longer the weakest force in certain contexts, violating the conjecture. Therefore, the universe must allow for a pathway, a quantum tunnel, through which our vacuum can eventually decay to a lower energy state. This places a strict upper limit on how long a universe like ours can last before it potentially collapses into a different vacuum. The incredibly small but non-zero value of our cosmological constant might be a direct consequence of this rule. It could be the longest-lasting, most stable value possible that still allows gravity to remain the weakest force. In this light, the fine-tuning is not a random accident, but the only possible outcome that satisfies the deeper laws of quantum gravity. The weak gravity conjecture transforms the cosmological constant problem from a question of why the vacuum energy is so small to a question of why it is the maximum smallness allowed by the laws of physics. Our entire cosmic epoch, with its gentle acceleration, might simply be the universe patiently waiting for its eventual, inevitable transformation. These elegant constraints from string theory might be the very reason our universe feels so finely tuned. The concept of the swampland offers a new way to distinguish between possible realities. It divides all conceivable theories of physics into two categories. On one side is the landscape, the set of effective field theories that are fully consistent with a complete theory of quantum gravity like string theory. These theories describe possible, stable universes. On the other side is the swampland, a vast bog of theories that look perfectly reasonable on their own, but are fundamentally incompatible with quantum gravity. They are mathematical dead ends, universes that could never actually exist. This is not just an academic exercise, it has a direct and dramatic impact on the mystery of dark energy. A set of ideas known as the de Sitter swampland conjectures place a severe constraint on the vacuum energy of our universe. De Sitter space is the name for an empty universe dominated by a positive cosmological constant, exactly the kind of accelerating cosmos we seem to inhabit. The conjectures suggest that such a configuration is highly unstable, if not impossible, within a proper theory of quantum gravity. Specifically, they propose that the energy of the vacuum cannot be a fixed positive number, but must either be exactly zero or be capable of decaying and changing over time. This directly challenges the simplest interpretation of dark energy as a cosmological constant. If these conjectures are correct, then our universe cannot be a truly eternal de Sitter space. The tiny, constant energy we measure must be an illusion, a temporary plateau on a much larger, evolving slope. This forces a dramatic rethink of our dark energy models. The cosmological constant would be ruled out, and we would be forced to consider dynamic alternatives like quintessence, where the dark energy field is slowly rolling down a potential, or even the phantom energy model, where it is evolving toward a future catastrophe. The swampland criteria become a cosmic litmus test. They tell us that if our universe is real and obeys the laws of quantum gravity, then the dark energy we observe cannot be a permanent fixture. It must have a history and a future, a beginning and an end. The acceleration we see today is not the final state of the cosmos, but merely a phase, a transient moment in a much grander cosmic story. The search for dark energy then transforms into a hunt for evidence of this evolution, a tiny but crucial drift in its strength over billions of years that would pull our universe out of the swampland and firmly into the landscape of genuine possibility. Symmetry is a silent architect of our universe, governing everything from the spiral of a galaxy to the spin of an electron. But what if this principle extends further than we ever dreamed, creating not just symmetrical shapes but a symmetrical cosmos? The mirror universe theory proposes exactly that, a hidden realm of particles that is a perfect reflection of our own. In this grand vision, for every proton, electron, and neutrino we know, there is an identical mirror partner. These shadow particles would form their own stars, planets, and perhaps even life, all operating in a parallel reality that shares our space but remains completely invisible. The only bridge between our world and the mirror world is the force of gravity. This single, fundamental connection is what makes the idea so compelling for the dark matter puzzle. The mirror particles would feel their own mirror forces, completely separate from our electromagnetism and nuclear interactions. They would pass through our world as if it were a ghost, utterly undetectable to our telescopes and particle detectors, yet their collective mass would exert a powerful gravitational pull. This mirror sector would naturally form vast, invisible halos around our galaxies, providing the exact gravitational scaffolding needed to hold fast-spinning stars in their orbits without a single particle of dark matter in the traditional sense. We would be living in a cosmic duplex, sharing a gravitational foundation with our silent neighbors next door. The implications for cosmic evolution are profound. In the early universe, the mirror world would have evolved in lockstep with our own, its particles freezing out to form its own dark plasma. The gravitational tugs between the two sectors would have subtly influenced how the first structures formed, potentially leaving a faint imprint on the cosmic microwave background or the large-scale distribution of galaxies we see today. This elegant idea answers a deep question about the nature of reality. Why is our universe so seemingly balanced, with matter and forces exhibiting such precise symmetries? Perhaps it is because the cosmos is fundamentally double, a perfect reflection where the missing mass of our world is simply the ordinary matter of another. The universe might be the ultimate free lunch. This theory proposes that everything we see, every galaxy, star, and planet, could have emerged from a random, fleeting tremor in a state of absolute nothingness. It all hinges on a bizarre quantum rule that allows for something to come from nothing, so long as it does not last too long. In the subatomic world, empty space is not truly empty. It is a seething foam where pairs of virtual particles and antiparticles constantly pop into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and paying back the debt. Our entire cosmos could be the result of the most monumental version of this event, a quantum fluctuation on a cosmic scale that, for some reason, never popped back out of existence. The key to this staggering idea lies in the concept of zero total energy. When you add up all the energy in the universe, the total might be precisely zero. How is that possible? All the positive energy locked in the mass of stars, planets, and dark matter is perfectly balanced by a vast reservoir of negative energy, the gravitational potential energy that binds the cosmos together. Think of building a tower from a pile of bricks scattered on the ground. The assembled tower has more order and potential energy, but to create it, you had to expend energy to lift each brick against gravity. In the cosmic accounting, the positive mass energy of all the matter is the tower, while the negative gravitational energy is the work it took to pull everything apart from a state of infinite density. They cancel each other out exactly. In this view, the Big Bang did not require a miraculous injection of energy. It was a quantum tunneling event from a primordial void into a state of zero total energy, a fluctuation that became our reality. This elegantly sidesteps the question of what came before, as time itself may have begun with that fluctuation. But it leaves us with a haunting question about the nature of that initial nothingness, and whether our universe is just one bubble in an eternal, frothing quantum sea where entire cosmoses blink in and out of existence. Could the universe require a witness to bring it into being? This idea pushes beyond the boundaries of conventional physics into a deeply philosophical realm where consciousness is not a mere byproduct of the cosmos, but a fundamental component of its structure. Certain interpretations of quantum mechanics have long wrestled with the role of the observer. In the famous double-slit experiment, particles seem to behave as probability waves, existing in multiple states at once until they are measured, at which point they snap into a single, definite reality. This has led some to speculate that consciousness itself is the agent that collapses the wave function, that the universe remains a blur of potentialities until a conscious mind observes it. Extending this logic to the largest scales leads to a staggering possibility. The precise values of the fundamental constants, including the incredibly small energy of the vacuum we call dark energy, might not be arbitrary. They could be the way they are because a conscious universe has, in a sense, chosen them, or because they are necessary prerequisites for consciousness to eventually emerge and complete the cosmic loop. This is not to suggest a human-like God, but rather that awareness might be a basic property of existence woven into the fabric of space-time. In this view, the fine-tuning is not a lucky accident but a cosmic necessity. A universe with a slightly stronger dark energy would have expanded too rapidly for galaxies and life to form, leaving no one to observe its emptiness. A universe with weaker dark energy would have collapsed back on itself long before sentience could arise. Our presence here, asking these questions, might be inextricably linked to the very physical laws we are trying to understand. We are not just inhabitants of the cosmos, we may be participants in its ongoing creation, and the missing energy we detect could be the signature of that profound, enduring relationship. Our reality might be the most advanced video game ever created. The simulation hypothesis asks us to consider that everything we know, from the farthest galaxy to the feeling of warmth from the sun, is part of an intricate digital construct. In this view, the cosmos is not a fundamental reality but a simulated one, running on a computer of unimaginable power in some higher base reality. If that is true, then the strange laws of physics we discover are not the bedrock of existence, but simply the rules of the simulation, the underlying code. This offers a startlingly different lens through which to view the mystery of dark energy. The fact that the vacuum energy is so small yet not zero could be a programming artifact. The creators of the simulation, whether they are future humans or advanced aliens, might have needed to fine-tune this constant to allow complex structures like galaxies and life to develop within their virtual world. A value too high would have caused the simulation to expand into meaningless noise too quickly, a computational failure. A value of zero might have been unstable or produced a universe that was not interesting enough to simulate. The precise, tiny number we measure could be the default setting, the optimal parameter for a long-running, stable cosmic simulation. The very concept of missing energy takes on a new meaning. In a simulated universe, there is no requirement for energy to be conserved in the way our in-game physics predicts. The apparent discrepancy between the energy we expect and the energy we see could be a glitch, a rounding error in the code, or a deliberate limitation to save on processing power. Think of a video game where distant landscapes are rendered with lower detail to prevent the system from lagging. The accelerating expansion of the universe driven by dark energy could be a similar optimization. As the simulation runs, the computational load of simulating an ever larger volume of space might become too great, introducing a force that pushes galaxies beyond the observable horizon. Could be the equivalent of deleting old files to free up memory, gracefully removing them from the active simulation to maintain performance. The other fine-tuned constants of nature, from the strength of gravity to the mass of the electron, would then be seen as the initial conditions loaded at the start of the program. They are not mysterious or lucky, they are simply the chosen parameters for this particular run. We are not living in a uniquely fine-tuned universe, we are living in a successfully booted one. This idea pushes the search for dark energy into the realm of the metaphysical. If we are in a simulation, the ultimate nature of dark energy is not a physical substance but a line of code. The greatest mystery of the cosmos would then have the simplest answer. It is not a feature of reality, but a feature of the program. From the cosmological constant's stubborn presence to the phantom energy of a future big rip, this journey through 30 theories reveals a cosmos far stranger than we ever imagined. We have explored the quiet hunt for WIMP and actions in deep underground labs, and we have scaled the wild heights of ideas where gravity is an illusion and our universe is a hologram projected from a distant surface. We have considered the possibility that we live in a cyclic ekpyrotic universe, forever colliding and reborn, and even confronted the mind-bending notion that all of this might be an advanced simulation. This incredible diversity of thought, from the well-established to the wildly speculative, is not a sign of scientific failure, but a testament to the profound nature of the mystery itself. The fact that over 95% of reality remains completely unknown to us is one of the greatest and most exciting puzzles in the entire history of science. It is a humbling reminder that the cosmos is still full of secrets, waiting for the next great mind to uncover them. So, after this tour of cosmic possibilities, which of these 30 theories resonates most with you? Do you find the elegant simplicity of the cosmological constant compelling, or does the cyclical drama of the ekpyrotic universe capture your imagination? Perhaps the radical idea of emergent gravity or the philosophical weight of the simulation hypothesis speaks to you. Share your thoughts in the comments below. The conversation about the universe's greatest mystery is just beginning.